Yeah. Okay. Hello. Thank you for the invitation. I'm going to tell you about joint work with my students Nicholas and Thilo on actually two different papers, where the first one deals with matchings, kind of related to the things we have just heard about, and then we generalize it to more general problems in a yet unpublished version of it. By now we have heard enough about matchings, so my, let's call it real world example is that of pirates. And as we know, every pirate needs a parrot, and you may have a compatibility graph, which pirate can deal with which parrot, and now you are obliged to assign each pirate one parrot. So that would be like these squiggly lines here. Pirate number one gets parrot number one, and so on. That's just a matching. In this special case, it's even a bipartite graph. We won't require bipartiteness in the following. So this is in particular a perfect matching. That is, every pirate gets a parrot and every parrot gets a pirate. And we are interested in this perfectness, that every vertex in the graph is in fact really matched. Now let's consider the multi-stage variant of it, which is very related to the temporal graphs we've just seen. You have different time slices, we'll call it years, and after each year the preferences between parrots and pirates may change, and you, in the beginning of each year, you can reassign the parrots to the pirates. So we start with the year one solution we've just seen, and then if we go to the second year, we can just use the very same matching again. That means we carry over all three edges. The intersection of these 2 years is 3. But now if we go to year number 3, we can see that this matching is no longer feasible because every pirate has a falling out with his parrot, and we need to figure out a different perfect matching, but now we cannot carry over any edges. We could have done a better solution. For example, if we go to year 2, we can use the very same matching that was already established in year 3. This would now give us a value of 3 moving from year 2 to 3, but year 1 to year 2 is now bad. But there we can use yet another matching so that we carry over 1 edge in the first transition and 3 edges in the second transition, and this would be best possible in that case. So this is the scenario we're talking about. We want to maximize the number of edges that carry over in the transitions under the restriction that in every year we want to have a perfect matching. In general, this is just the general notation that we use. We have different edge sets for each year on a common vertex set, but these graphs need not be spanning. And each year in the previous example is what we call a stage now. So we have a multi-stage graph. 3-stage graph has 3 different graphs in it. So we are asking for a multi-stage perfect matching, which means in every stage we want to have a perfect matching, and the profit we consider is the intersection between 2 consecutive stages, and we just sum up overall these transitions, and that's what we want to maximize. Finding this best solution is and be hard. You can deduce that for 6 stages and above already for quite a couple of years. Bumpus et al. Have shown that it suffices to have 2 stages at least, and it becomes hard. And we strengthen that a bit more by showing that actually 2 stages and maximum degree 2 in each stage is already enough, because each of these 2 stages will just consist of a set of disjoint cycles, and already then the problem turns out to be hard. There is research on a very related topic the maximum multi-stage matching problem, which is also shown to be APX hard, that shows that you can approximate it within a ratio of 1/2. What you do there is you do not only consider the transition costs P of M, but you also consider the size of the matchings that you find in each of the stages. So the question is, does that not include our problem then? Well, it does not directly. Think about this instance here. You're going from year 1 to year 2 and year 3, and if you are forced to pick a perfect matching in each year, then the best you can do is you have a transition of profit 1 in the first transition and of profit 1 in the second transition, just because that's how the graph was built. So the objective function in that setting would be the transition cost 1 plus the transition profit 1 plus the matching benefits that you have in each stage selected 3 edges. Now, if you drop the requirement of having perfect matchings, you could do better. In the second year, you can just not pick a perfect matching. You just pick the top edge instead. So you only select 2 edges, so the matchings get worse, but the transitions get better because you can now carry over 2 edges each. So if you just use this scenario, you will not get to guarantee perfectness. Well, you could if you just add high enough weight to the edges, right? Because then you would be forced to pick a perfect matching in each stage. But then the approximation ratio of 1/2 doesn't tell you much any longer, because the main body of volume that you generate in your objective function will just be these huge values for the matchings if you give them high weight, and it doesn't matter anymore how good the transitions are. So it's rather simple then to get a good approximation ratio in that sense without doing anything about the transitions at all. So what we are really interested is we want to have approximation guarantees under hard constraints for each stage. So these transitions should be very well, even if we are required to have a perfect matching in each stage. One of the key workhorses in our algorithm is the concept of proficiency, which is just an amalgamation of 2 words, preference and efficient. This is something we call a problem proficient if we say we can solve the problem efficiently, that is in polynomial time, while adding some preferred elements to it. So in terms of matching, that means you're given a graph, you want to compute a perfect matching on a graph, just a single stage graph, and I also give you a subset of the edges which are to be preferred. And now I ask for a perfect matching where you select as many of these preferred edges as possible. And this is, of course, very trivial to do for a perfect matching, because you can compute the maximum weight matching in polynomial time, and just for the edges that you prefer, you give them a slightly higher weight than the other edges, and then this is just what comes out. You will get a perfect matching with as many preferred edges as possible. So that's very trivial to do, and therefore to see that perfect matching is so-called proficient. There is another measure that we will use in the following, that's something that we call intertwinement. The question is, if you have multiple graphs from one stage to another, how much do they change? Of course, if 2 consecutive stages have no edges in common, there is nothing that you could really optimize the intersection to be large of. If they have many edges in common, the problem becomes more difficult. So the intertwinement just measures the intersection size of the 2 edge sets between consecutive stages, and you just take the maximum over all the stages there. I'll now show you the idea of how we approximate our problem for the two-stage case first. In the two-stage case, we have two edge sets, E1 and E2. These are the edge sets of the first and the second stage. And ECAP in violet here, that's the common edges between the two stages. And we start with preferring all of these edges. And then we do a very, very simple idea, which in the first step would not yield any approximation guarantee. You just try to find a matching in the first stage, which uses as many edges of the common edges as possible. Very naive to do that thing. That's just what you would normally do if you hear about the problem the first time. Now, this gives you a matching M1 in the first stage, and now you find a matching M2 in the second stage, and there, very naively, you just ask for a matching in the second stage, which picks as many edges from M1 as possible. So you get the highest overlap possible. That's really all there is. This by itself would not yield any good guarantee. Now what we do is all the edges that we have seen in our matching M1, we remove them from the set P, so from the preferred edges, and then we just iterate that process. We again look for a matching M1 in the first stage, which takes as many of the still preferred edges. Then we try to find that M2, which gets a large overlap with it, and we just iterate that all the time, removing the seen edges until all of the edges that are common between the two stages have been selected in M1 at least once. Each iteration gives me a candidate for a solution, because each iteration yields a matching in the first and in the second stage, and I just return that pair of matchings that gives the best profit. And what we can show is that this algorithm yields a tight approximation of ratio 1 over the square root of 2 chi, which is just chi is the intertwinement of the graph. What is the idea of proving that? Well, assume you have the optimal matching in the first and the second stage, which yields the largest possible common matching edges, M star cap. And we can assume that this includes at least one edge, otherwise every algorithm will yield the zero solution. And we can now distinguish whether this optimal solution is large or small. If the optimal solution is small, less than the square root of 2 chi, then, well, any solution which has one edge in common already attains the approximation ratio. We can trivially achieve that with our algorithm, so there's nothing to prove in that case, really. So now we have to consider the case that the optimal solution is large. Well, if the optimal solution is large, but our algorithm does not find it, then that means that in each iteration, the algorithm will just peel off few of the optimal edges to its set M1. So it only takes away few edges of those really good edges of the optimal solution, which then in turn means that we have to have very many iterations in our algorithm, because our algorithm runs as long as there is an edge that has not been seen by the matching M1 first. So these good edges that we would actually want to pick but don't know about, we only get few of these edges in each iteration. We have many iterations, and so this number decreases only very slowly. But at the same time, the matching M1 in our algorithm that we find prefers all these good edges. So if you combine that the matchings always have to be large, but only few of the good edges are selected, then you can deduce that at some point, all the preferred edges that were not so good have already been eaten away by our algorithm, and the algorithm has to pick a large solution close to the optimal. And if you then realize that the second matching is always perfect with respect to, or best possible with respect to the matching M1 that our algorithm selected, then you can just by applying a couple of algebra sentences, you can just deduce our approximation ratio. That turns out to be tight, actually. There are a couple of more results we have there. Most importantly, we can transform any two-stage approximation into an approximation for arbitrarily many stages, and the approximation ratio only goes down by the factor of 1/2. So we have seen that we can approximate our problem with a ratio of 1 over square root of 2 chi. So for an arbitrary number of stages, you just substitute the 2 with a 4 because it's within the square root. And that's the approximation ratio you get for an arbitrary number of stages. And in fact, it's even stronger in a certain sense that you can transform any instance with many stages into an instance with only 2 stages, and you have an S reduction in the sense that they attain the same objective values. So if you would have an approximation ratio that is constant, then it doesn't matter whether you're looking the 2-stage version or the many-stage version. This function, of course, looks kind of ugly. I mean, 1 over square root of 2 chi, that's not a nice function, right? But it may be unavoidable. We only have a hint for that. If you look at the natural LP relaxation for this problem in 2 stages, then you can see that it already has an LP gap in the order of square root of chi. So we are just a constant off of that LP gap. So it may be necessary to have the intertwinement in the approximation ratio, but perhaps not, who knows. There is also the related problems of when you do not want to maximize the intersections between consecutive stages, but you want to minimize the union. And we have a couple of approximation results there as well, but I will not go into details for that because I want to jump to the topic of generalizing these algorithms now. Consider any subgraph problem. What is a subgraph problem? Well, there is a formal definition for it, but the gist of it is just you're given a graph and you want to find a subset of its graph elements, be it edges, be it vertices, I don't care, and you want to optimize some measure. Matching is an example for a subgraph problem. So is the shortest path or vertex cover independent set, maximum planar subgraph, anything where you select a subgraph of a given graph. That's a subgraph problem. And we can just define for any given subgraph problem the multi-stage variant of it, where in our setting, we say that we have multiple stages. In each stage, we have to solve a subgraph problem, and we want to solve that subgraph problem optimally. So we want to have an optimal solution in each individual stage. And within that realm, we want to maximize the transition profit. And now we can take this algorithm that I've shown you before, and of course we have to build it out a bit to handle all the general things that can happen but do not occur with the matching. But we can attain the same approximation ratio for any multi-stage subgraph problem, provided that this multi-stage subgraph problem is proficient. Recall, proficient means that the subgraph problem can be solved in polynomial time because we want to have an optimal solution in each stage. So this needs to be polynomial time solvable. And it can be solved in polynomial time such that I can give you a subset of graph elements, edges or vertices, and the solution, and these elements will be preferred in the solution. And it turns out that proficiency is rather trivial to show for nearly all proficient subgraph problems. Essentially, all you have to do is you just add an epsilon to weights or some similar construction. So this is really a very simple step that allows you to use our approximation framework to deduce approximation results for any proficient such multi-stage subgraph problem. And this includes the multi-stage version of the shortest path problem, of the minimum cut problem, of the maximum cut problem, provided that maximum cut is polynomial time, as it is on planar graphs, on bipartite graphs, on the generalization of both of them, the weakly bipartite graph, an awful name, by the way, and the minimum weight vertex cover restricted on bipartite graphs, maximum weight independent set on bipartite graphs. All these problems are proficient, and therefore you can get these approximation ratios directly out of the box. So to summarize, what we are really interested in here is we want to approximate such multi-stage problems with the restriction that we have an optimal solution in each stage, and under this restriction we want to have good guarantees for the transitions between these optimal solutions. The central question is whether this dependency, it's a rooted dependency, but is a dependency on the intertwinement of the instance, if this is really necessary or not. We do not know. We have hints that it may be necessary because of the LP gap, but that's a rather weak hint, if you want to call it that. It may be that there is a constant factor approximation around there. We just don't know it. Is it best possible for general multi-stage subgraph problems? Is it best possible for matchings? Can we do better on matchings at least? I don't know. And then there is a weird question, which is probably food for thought. I'm not sure if this question makes sense. It's just the opposite of what we are doing. What we are doing now is we want to have optimal solutions in each stage and then try to find as good transitions as possible. You could turn it around. You could ask for, you want to have feasible but non-optimal solutions in each stage, and you want to have perfect transitions. In certain problems, this becomes a trivial problem, but not always. Is there something interesting in there? That's the question. Thank you very much for your attention.